Reactions that follow second-order kinetics are going to be some reactant forming products where the rate of the reaction is dependent upon the concentration of reactant A to the second power. So our rate law equation would be R equals K times the concentration of reactant A squared. We could also see reactions where we have two different species reacting, we'll call them A and B, going to form our products. And in this case, our rate law equation would be R equals K times the concentration of A times the concentration of B. Both of those would be to the first order. So overall, since both of those are to the first order, the equation would add up to having second order kinetics overall. We're going to focus on the first case scenario where we have one reactant that has second order kinetics itself. The integrated rate law for where we have one reactant with respect to time ends up being 1 over concentration after some time equals K times T plus 1 over the original concentration A sub 0. The decomposition reaction 2NOCl forming 2NO and Cl2 has a rate law that is second order with respect to NOCl, where the rate law constant K is equal to 3.2 1 over molarity times seconds at a certain temperature. If the initial concentration of NOCl is 0.076 molar, how many seconds will it take for the NOCl concentration to decrease to 0.042 molar at this temperature? So since we know that this is a second order rate law, we're going to use the integrated formula for second order. 1 over AT equals K times T plus 1 over A sub 0, the original concentration. And in this case, we know a few things from the problem. We know our original concentration is equal to 0.076 molar. We know our concentration after some time has passed, A sub T, is 0.042 molar. We also know that our rate law constant K is 3.2 1 over molarity times seconds. The units here also match for a second order integrated rate law. We're trying to figure out what the time or lowercase t is. So we can rearrange our formula to solve for t. T will be equal to 1 over AT minus 1 over our original concentration divided by K. So now we have to plug everything in to our formula. 1 over A sub T will be 1 over 0.042 minus 1 over our original concentration, 0.076, divided by 3.2 for our K value. Our time in this case is going to end up being in units of seconds because those were the units that were associated with our rate law constant. So T will come out to being 10.65 in the numerator divided by 3.2, which will be 3.33 seconds. The reaction of butadiene gas with itself produces C8H12 gas as follows. 2 times butadiene gives us 1 C8H12. The reaction is second order with a rate constant K equals 5.76 times 10 to the negative 2, 1 over molarity times minutes, under certain conditions. If the initial concentration of butadiene is 0.2 molar, what is the concentration remaining after 10 minutes? In this case, we know that our A sub 0, our original concentration, is 0.200 molar. Our rate law constant K is equal to 5.76 times 10 to the negative 2, 1 over molarity times minutes. Our time in this case is equal to 10 minutes. So our units match between our rate law constant K and the time we were given. We don't have to convert anything there. What we're trying to figure out then is our concentration after that time has passed, or A sub T. So since we know that this is a second order reaction, we're going to start with our second order integrated rate law. 1 over AT is equal to K times T plus 1 over our original concentration, A0. We can plug in everything on the right-hand side of the equation. We know what K is, 5.76 times 10 to the negative 2. We know what T is, 10 minutes, plus 1 over our original concentration, so 1 over 0.200. That will give us 1 over A sub T. So when we plug all that in, 1 over A sub T comes out to being 5.58. In order to get AT out of the denominator, we have to take the inverse of that number. So concentration after time will equal 1 over 5.58, or 0.179 molar. And you can check and make sure that it makes sense. You got a concentration that was less than your initial concentration of 0.2 molar. If you had gotten something that was a higher value, you would have known that you made a mistake somewhere along the way. So always look for a concentration that's lower than what you started with if you're figuring it out after some time has passed. You could also be given data that you need to graph in order to answer if an overall reaction follows second order kinetics. Notice that the second order integrated rate law is in the form of slope-intercept. We have y equals mx plus b. So on the y-axis, we would have 1 over concentration. On the x-axis, we would graph time. And our slope, or m, is equal to the rate law constant, k. It'll cross the y-axis at 1 over A0, or 1 over the original concentration, which is the b-intercept. In this case, our k value is positive, so our slope is a straight line with a positive slope here when we graph 1 over A on the y and time on the x. When you make this plot, if you do get a straight line with a positive slope, that tells you that the kinetics do follow second order. If you make this graph and you get anything else, if you graph 1 over concentration and you graph time, and you were to get a straight line with a negative slope, you can't say that it's first order because you're not graphing the correct things on the y-axis for first order, but you can say that it's not second order. So the only thing that you can get that will match second order kinetics is this straight line with a positive slope right here that's equal to the rate law constant. So you could also use this to solve for an unknown rate law constant after you make the graph, if you figure out what the slope is. We can use these different plots in order to determine if a set of data is first order or second order. So imagine that we have some experimental data versus time for the decomposition of gaseous dinitrogen pentoxide at 55 degrees Celsius. Is the reaction first order? What is the value of the rate law constant? In this case, we want to solve for that. So if we want to answer if the reaction is first order and we're given time information and concentration information, recall that the first order integrated rate law equation is the natural log of concentration equals negative K times T plus the natural log of our original concentration. That's written in slope-intercept form. So we had y equals mx plus b. In this case, we had to graph on the y-axis the natural log of concentration, and on the x-axis, we had to graph time. So if we're going to answer, is this reaction first order, we first need to take the natural log of all of our concentrations right here. Once you take the natural log of all of those concentrations, you're going to notice that you get negative numbers for them. So we're going to plot on our x-axis time and on our y-axis natural log of concentration. If we get a straight line with a negative slope, we can say that the reaction is first order. If we get anything else, we can say that the reaction is not first order. So using Excel to plot that data, we have our natural log of the dinitrogen pentoxide on the y-axis, and we have time on the x-axis. And notice that these values are getting more negative here, and they're getting more positive in this direction along x. So you're plotting down in the fourth quadrant right here, if you think about your quadrant system. And what did we get? We got a straight line and it has a negative slope. So in this case, because we have that straight line and negative slope, we can say that negative m is equal to k, our rate law constant, using our first order kinetics integrated rate law. Ln of at equals negative kt plus ln of a0. So when we graphed that data, we did get what we were expecting. We can say that this is a first order equation. If we had gotten anything else when we plotted this data, so if we had plotted ln of at versus time, and we had gotten a straight line but a positive slope, all we could have said for that is it's not first order. We could not have said that it was second order from that because we were not plotting 1 over concentration. We were plotting the natural log of concentration. So you want to know what you would need to plot on the x-axis and the y-axis for each of the different integrated rate laws and what your line or your slope should be equal to if it is that specific order. The last type of kinetics we'll talk about are zeroth order kinetics, or zeroth order reactions. These are reactions whose rate is independent of the reactant concentration. The rate of the reaction will remain constant throughout the reaction. If we imagine we have reactant A forming products, we would say that R equals K times the concentration of A raised to the zeroth power. But anything that's raised to the 0 power is actually equal to 1. So really this reduces down to R equals K times 1, or in other words, the rate is equal to K, the rate law constant. So rate is unchanging throughout the rate of the reaction. Normally the rate varies as the reaction progresses, but not with the zeroth order reaction. The rate stays the same and it's always equal to K, the rate law constant. The integrated rate law, when we integrate this form, and we use calculus to integrate it to this form for a zeroth order reaction, is the concentration of A sub T is equal to negative K times T plus the concentration A sub 0, the original concentration. This is already written in slope-intercept form. So we have Y equals mx plus B. Our Y, we would graph the concentration. On X, we would still graph time. And we should expect for our slope a straight line with a negative slope equal to K. So here we see the graphical version of a zeroth order reaction. On the y-axis, we just have concentration, not 1 over concentration or not natural log of concentration, just concentration. And on the x-axis, we have time as usual. Normally, what a plot looks like for any other order reaction, when you look at concentration versus time, is you see a decay. You see exponentially the reactant disappearing until it eventually is all used up and it goes away over time. There's not some nice linear relationship between most kinetics when you just plot concentration versus time, which is why we usually use the integrated rate laws to have plots that give us straight lines that you can abstract data from. It's a lot harder to pull any useful information from an exponential decay than it is from a linear. Whereas we have a zeroth order reaction here, and we have concentration versus time, but we end up having this nice straight line. And this is because the rate of the reaction is constant throughout the reaction. It doesn't matter the concentration. The concentration doesn't affect the rate, since the rate was equal to the rate law constant. Our m term, or our slope, is equal to negative k. So we've got this straight line with a negative slope here, and we could use it to solve for the rate law constant of a zeroth order reaction. Usually a zeroth order reaction will be part of another reaction where you have multiple reactants, and maybe one reactant is first order and another reactant is zeroth order with it. So both reactants are important, but the zeroth order component doesn't influence the rate overall. It keeps constant throughout. So usually you don't have a species that is zeroth order reacting by itself.